Hi everyone. Almost every computer that we use nowadays, it has become heterogeneous in terms of the hardware that exists inside it. Multi-core CPUs, GPUs, and FPGAs, they have been resources that can facilitate parallel programming and increase the performance of our applications, while also reducing the energy costs. Now, the utilization of these resources in programming languages that they have built on top of a runtime system, which is in a sense they have been designed for single-threaded CPU execution, it has been challenging. That has motivated our team at the University of Manchester to develop TornadoVM. TornadoVM is an open source software technology that can accelerate JVM applications on heterogeneous hardware accelerators. This is the agenda for today. I will start with a description of the problem and the objective of our team, in a sense the motivation. Then I will show you TornadoVM. I will present some factors and classify them in categories, some factors that can impact performance of applications. Then I will show how TornadoVM can be used by programmers to accelerate their Java applications and how it can be employed within existing Java code bases. And finally, I will close this talk with a description of the use cases that have already piloted TornadoVM. Let's start with the problem. Hardware acceleration is a way to increase performance of software applications. Now, although performance can be increased, and this can be significant for our applications and our projects, this can come at a cost. The first cost can be the development cycle, so in a sense the time spent by a team of engineers to develop the actual solution. And the second one is the operational cost, which regards the actual resources that the company has to afford in order to deliver the actual product. Now, in our team, our objective is to enable with our software high performance while reducing these costs. And this can be achieved with TornadoVM, our runtime and compiler that can automatically generate heterogeneous code that can be offloaded on GPUs, FPGAs, and multi-core CPUs. Okay, let's have a flavor of TornadoVM. TornadoVM is a plugin to different JDKs, including OpenJDK, GraalVM, Amazon Corretto, Red Hat Mandrel, and Microsoft JDK. And recently, it supports JDK 17. TornadoVM currently targets different heterogeneous architectures, and we support 3 backends to do that. The first backend is OpenCL. The OpenCL code is portable to run on multi-core CPUs, GPUs, and FPGAs. The second backend is PTX, which in a sense it is the assembly code for NVIDIA GPUs. Now, for these 2 backends, TornadoVM generates a source code, a C code in a sense, or an assembly code. While for the last backend, which is PV, TornadoVM generates binary code. TornadoVM currently can compile Java bytecodes to OpenCL, PTX, and SPIR-V. However, with the interoperability that we have with GraalVM, we can enable any programming language that can run on top of Truffle with the Polyglot API to leverage the acceleration of Java. And this can increase the performance of these programming languages also. Our code is available on GitHub. It is open source. We encourage you to fork it, clone it, try our examples, or code your own examples with your own applications. You can also download our Docker images that we have available in Docker Hub. And we have images for NVIDIA GPUs and Intel integrated CPUs. Let's have a look to the TornadoVM features. Recently, we enabled the TornadoVM installer, which is an installation script in a sense that can enable users to install TornadoVM without the need to care about the dependencies. Now, this has been integrated in the TornadoVM repository and enables users to just pass a flag, for example, which JDK version they want to configure TornadoVM to run, and also which backends they would like to enable TornadoVM to use. For example, they can use OpenCL configuration, PTX configuration, or SPIR-V configuration, or all of them to enable TornadoVM to emit code for all the backends. Now, this script can run on Linux and Mac OS, and the majority of the code that we have developed and we have tried, it is on Linux operating systems. However, we have tried our examples and our unit tests in the Mac OS and in Windows OS, for example, Windows 10 recently. However, this path for the last two operating systems, it is currently experimental. Now let's have a look on what we believe as a team that TornadoVM can offer to Java developers, which in a sense it is transparent acceleration. We want TornadoVM to enable Java programmers to code parallel code, however, without requiring to have any knowledge about hardware or computer architecture. And in a sense, we achieve that through the different OpenCL, PTX, and SPIR-V backends that we have, and without exposing any information about these backends to the users, but only exposing an API that can enable them to code in parallel. Everything is hidden under our compiler. In a sense, TornadoVM abstracts all this information regarding hardware architecture by emitting code and applying automatically transformations of the code at the compiler level. So in a sense, we have a hardware agnostic API that enables developers to express parallelism, and our TornadoVM compiler that enhances the code and emits code optimized for GPUs or optimized for FPGAs transparently to the user. And this results in transparent acceleration. Let's have a look now. I want to show you an example. This snapshot is from the terminal on my machine. And in this machine, I have installed TornadoVM with the OpenCL backend. And this can be reflected on the first number here in this identifier, which is 0. In a sense, there is only one driver, Tornado driver. It is OpenCL, which is represented to the backend. And then there are two devices, two OpenCL compatible devices. The first device discovered on my machine, it is the Intel CPU, while the second one is the Intel integrated graphics. With this command, tornado -- devices, users can see how many devices exist on the system and how many devices TornadoVM has discovered, where they can offload their code. Now, if I wanted to run an example of a matrix multiplication on a heterogeneous resource on my machine with TornadoVM, I would use Tornado and then the class name. Tornado is an alias for the Java binary along with all the flags that enable Tornado to compile and use acceleration. And the same command can be used to target different hardware resources, CPU, GPU, and FPGA. The only difference is that, as it is right now, this command would run on the first device because this one is the default one. But this can change either by using a flag on the command, on the command cell, or by configuring that on the source code, or by configuring TornadoVM, in a sense, to decide on which device it would be better to run. For example, based on performance or latency. More details there on a repository, and this is called the dynamic reconfiguration feature. Let's have a look now about the factors that can impact performance of applications. In this slide, I want to classify these factors in three categories. The first one is the algorithmic part, which in a sense regards the pattern of an application, how it is coded. Some code segments within the code can be expressed to run in parallel because there is no dependency. And then the second aspect is the actual data sizes. If the sizes of the parallel part of our application is very small, then maybe it doesn't worth to go to a GPU. for the actual computation, because then the actual cost to move data can be higher than the actual merit that we can get from the acceleration. And the last aspect is regarding the data types. We have seen with our team that for GPUs in particular, some precision, for example, using double types, can result in slower performance than float types. So if you want to get more precision in the floating point arithmetic, that can sacrifice performance. The second category regards software configuration. We are working on a JVM, so we know that the heap size, if you have a small heap size, that can trigger garbage collection more often. And then you want to ensure that the code has been JITted, so you need to perform some warm-up in order to ensure that the code will not run in the interpreted mode. And finally, we have the hardware configuration category. So in this category, I want to focus on the PCI Express, which in a sense it is the interconnect that we use. And we want to ensure that we saturate in a sense the bandwidth of the interconnect that we use in order to achieve high performance for our application. This happens if our application has a lot of data that we need to move to the device, to the memory inside the device. Yeah. And then the last one is the kernel. The kernel regards the actual code that will run on each thread of our device. For example, for a GPU, the kernel can be the instance of code that will be executed by each thread on the GPU. And this regards the actual locality of the kernel. So in the GPU architecture, there is the GPU memory hierarchy. So in a sense, there is some memory, the local memory, that can be used as a cache memory to hold data that can be accessed by a group of threads. And the other parameter is the deployed threads. So we have seen that if the number of deployed threads on the GPU is not the power of 2, then this can result in performance degradation. Now, a rational question that emerges, it is how can we determine if an application is suitable for acceleration? And the answer to that is by profiling. In this slide, I will use an example, DFT, which is an algorithm that is used in digital signal processing and image processing. I use 1 megabyte of data as the data size, and I configure my JVM, which is OpenJDK 17, to use 2 gigabytes as heap size, and I have warmed up. And I use as a profiling tool the async profiler, but it could be any JVM profiling tool. And in this case, I have implemented DFT in Java. And in my class, the DFT Java class, I have the compute DFT method. And the majority of the time, the 99.99% of the time is spent on this method. This indicates that this method is compute intensive. And then I use the TornadoVM and the parallel implementation that we have implemented in our repository for the DFT. And I run on an NVIDIA 1050, which uses the PCIe with generation 3 and 16 lanes. And then I used as the number of threads that I deploy on the GPU, the number of elements for the 1 megabyte of the data size. And this resulted in 4,297x performance improvement, which indicates that indeed the actual algorithm is compute intensive. Now, once we have run on the hardware, TornadoVM exposes a tool, the profiler, which enables users and programmers to understand better the behavior of their code. Now, this tool can be enabled by using this flag, the enable profiler, which is accompanied by an option. In this case, I use console, which will display the actual profiling information in the console, but it could be used also the silent mode, which would write a file in a JSON format. And here we see all the different information that the TornadoVM Profiler exposes, which is the actual kernel execution, then the dispatch time for the kernel and data transfers, then the copying time, the actual Tornado task schedule time, which is the end-to-end time, and the copy out time, the actual number of bytes that it is copied in and out, the name of the method that is accelerated on the GPU, and then the information about the device, which device it is, and which one is the actual identifier of the device. Now in this case, I have created this table just to indicate that the kernel time reported by TornadoVM, it reaches 98% of the total end-to-end time. Then some time is spent on the dispatching, which in a sense it is the time spent when TornadoVM issues a command and queues a command to the OpenCL or CUDA command queue until the actual command will be executed by the driver. And then copy in and copy out regard the actual data transfers from the CPU to the GPU memory and from the GPU memory back to the CPU for the actual result. And the rest of the time is spent for in the runtime. Okay, now let's provide some background regarding the heterogeneous programming models. I will focus on OpenCL and CUDA because these two are, in a sense, supported by TornadoVM. However, this can be applicable on others. In these cases, we have, let's say, one program, and this program can be split in two parts. The host code, which is the actual application that is written in C++, and then it is the kernel code, which is the actual compute function that will be offloaded on the device. And this part is in a sense the compute intensive part because it can offer the performance. Now, the execution model of both OpenCL and CUDA, it is similar and includes three steps. The first step is to move data from CPU to device. In this case, I say Java because the Java is the one that it is the host code in our case in TornadoVM. So we move the data from our Java world to the device memory. These are the data that will be processed. The second one is the parallel computation, which is the actual computation of the data. And the final one is copying back the resulting data from the device memory back to Java. Here now I will show you how you can use TornadoVM to program your Java applications. We have this in our mind, the slide that I showed you earlier regarding OpenCL and CUDA programming models. Now let's see the Java world. In our Java applications, we would have, let's say, a class with multiple methods. We could use the profiler to find which methods can be accelerated or would be worthy to be accelerated. And let's say in this example, we have n methods that can be accelerated. Then TornadoVM exposes a task. In a sense, a task corresponds to each method that can be accelerated. And the task, it is, let's say, an object that we use in TornadoVM to indicate that a method should be compiled to OpenCL, SPIR-V, or PTX. And this task can be inside a task group, so the task schedule. The task schedule, it is an object that chains tasks to be executed on a device. In a sense, it provides developers with a tool that they can orchestrate if there are dependencies between the methods in order to ensure that they can be executed in the right order. Now, once we have talked about the host code, which regards the task schedule and the task, let's move to the actual APIs that are exposed by TornadoVM to enable Java programmers to express parallel execution in their Java applications. We have two APIs. The first one is the loop parallel API, which in a sense exposes an annotation to Java programmers that they can use to indicate that for loops can be executed in parallel. And this can be done through the @parallel annotation. The second API, it is Kernel API, and we have designed this in order to give to programmers more freedom regarding the OpenCL and CUDA features that they can exploit. In a sense, this is designed for either for programmers that they have OpenCL and CUDA expertise and they know what they are doing. If they want to use, for example, local memory, they can use this API. Or for programmers that they don't have this experience, but they have some code, let's say some existing kernels written in OpenCL, and they would like to exploit them from Java. So this gives them the opportunity to rewrite them with Java. And in a sense, they can use the kernel context API, the kernel context object, that exposes all these features. I will show you an example to make it clear. In this example, we have implemented matrix multiplication in Java. We use the primitive types. In a sense, all our arrays are float types. And we have two parts in this in our class. The first method corresponds to the actual computation of the matrix multiplication, while the second one is the host part, which performs all the initialization of data and the declaration of the matrices. Now here is the vanilla host code of the main method, and I will show you now. Let's remind the actual execution model of OpenCL and CUDA, and now I want to show you how programmers can use the task schedule API to express this execution model in Java. At first, they have to create the task schedule object. The task schedule is the object that inside it has the number of tasks that can be offloaded on a device. The first step, it is to declare which data have to be copied in the device memory. The second part is the parallel computation. So in a sense, we use the task method to declare which method in our program will be compiled to a kernel to be offloaded on a device. In this case, it is the matrix multiplication. And the last one, it is the stream out, which declares which data will be the actual result of the computation, and we need it back to read it in Java. Now I wanted to say that we declare here the strings S0 and T0, and this can be used earlier when I said that we can use in the command in our shell to declare in which device we want to run. This information can be exploited by programmers. We have some examples in our website in GitHub. And the last part, it is the execute method. So the execute method is the actual launching of the execution, which it is mapped, let's say, to the actual invocation of the matrix multiplication when we run in Java. So the execute method will start the execution in the device. Now let's see how we can express parallelism with the first API, the loop parallel API. In this case, we have the vanilla matrix multiplication implemented in Java, and the programmers, they have to use the @parallel annotation in order to indicate that these loops can run in parallel. Now in this example, the actual loops, they don't have any dependency. So TornadoVM will create a parallel implementation that can occupy 2 dimensions as they are expressed in the GPU hierarchy. Now let's have a look how the second API can be used to express parallelism, the Kernel API. At the top we have the loop parallel API, and I want to show you how the Kernel API can be used for the same example. So in this case, we see here that we have the two for loops. So in this case, we use the kernel context object, which exposes the kernel API, and we actually use the context global IDX and global IDY, which correspond to the actual thread identifier in each dimension. Now, I said earlier that in this example, Tornado will result in using two dimensions. So in a sense, the first dimension would use identifiers like being identified by I, while the second one will be identified by J. Now in this case, we replace completely the for loops, and we actually have the identifier of each thread in global row and global call. And then it is the actual body of the for loops that follows. This, in fact, the second part, the second matrix multiplication implementation, corresponds to how a kernel would look like if we were using OpenCL or CUDA to write it, but it is written in Java. Now I want to show you an example of matrix multiplication, but while using also some optimizations that I have not implemented, and I have used them from this website. So in a sense, this is a snapshot of a matrix multiplication implementation that uses local memory and loop tiling, which are two techniques that can improve the actual accessing of data from the memory within the kernel. So in this case, we implemented the matrix multiplication using the kernel context, which is the object for the kernel API. And then we have used the local identifiers, the group ID, we have allocated the local memory, but in a sense in Java it is this allocation is flattened. And then we have the actual barriers that we used before the actual computation on a single tile. And now that we have shown how it can be implemented, this part it is when you have, let's say, an existing kernel in OpenCL or CUDA, you can actually code it in Java. And when you have TornadoVM, this Java code can be translated, can be compiled back to OpenCL again, PTX or SPIR-V. But let's talk about performance now. In this experiment, I used the Java implementation and I compared it against the loop parallel API and the kernel API implementations. The kernel API is the actual implementation that uses the loop tiling and local memory optimizations. In this case, as data size, I used 2048 elements for the matrix per dimension, for 2 dimensions. And we see that the actual implementation, the actual execution time of the code has been reduced from 35 seconds to 231 milliseconds. So in a sense, it results in 153x performance improvement. Now we will move to the part that I will show you how TornadoVM can be integrated in existing projects. So TornadoVM can be used either in external projects. So in a sense, external projects can use TornadoVM as a library in order to use the API for acceleration. Or you can use TornadoVM in sandboxing mode. So you can clone it, you can do your own experiments within TornadoVM repository, your forks, and you can also open PRs if you have contributions. Now the first part regarding the external projects, you can copy this part, you can add these dependencies in your Maven by copying this part to your POM XML files of your projects. And I have to say that the API of Tornado is licensed under Apache 2. Now regarding sandboxing, in our GitHub repository, we offer some instructions how to integrate IntelliJ and how to use the formatter of our code base to IntelliJ and Eclipse. And this will allow you to use our formatter in order to ensure that you can contribute to our repository and you can open the PR. Now that I have said about PRs, let's see how you can contribute if you are interested. So we encourage you to try our code. When you try the code, to use GitHub issues. Issues can be used either to declare a bug, or you can use the GitHub discussions to actually ask questions about TornadoVM. We are very interested in improving our documentation, so we encourage you to come back to us with some comments and give feedback. We're very interested in getting some new use cases to see how TornadoVM can be used in different use cases for acceleration. We perform, usually in each year, we release 4 versions of TornadoVM, 4 new versions. The next one will come in March. And in each version, we include some new bug fixes, so stay tuned. And if you are interested to contribute to the actual core of TornadoVM, which is the compiler and the runtime, feel free to share a proposal as a Google Doc, which we can review and we can give feedback, and we can help you design an architecture, how to implement it, and then this can result in a PR on our public repository. More information exists in this link. Now the last part of my talk, it regards the use cases. Here is a brief description of the use cases. As we see here, we have many application domains that TornadoVM has been used for acceleration. The first 2 regard the actual computer vision applications and face detection. And then we have natural language processing. We have seen TornadoVM accelerating the training of a machine learning model by utilizing GPUs. And the last part regards the actual analytics of data that have come from IoT sensors. More details about these areas exist in the TornadoVM website. Our team is based on academia, and in fact these 2 photos are from the campus of the University of Manchester, and we have many alumni that they have contributed, and we would like to acknowledge them. Finally, I want to ask if there is anything that we can do for you. Please contact us either with the TornadoVM link or through my email. We're very interested to discussing about potential collaborations or ways to improve TornadoVM. So yes, please come back to us. And finally, to wrap up, today I presented you the objective of our team, which is to propose TornadoVM as a way that can increase performance while reducing the actual development and operational costs through the abstraction of hardware resources and how we can program the hardware resources. Then TornadoVM is open source, so feel free to clone it and try it if you are interested. I have shown you some examples how to use the 2 APIs that we have in TornadoVM to express parallelism. The first one is the loop parallel API, which has an annotation for loops, while the second one is the Kernel API, where programmers can exploit more low-level features available in OpenCL or CUDA. And finally, I show you some of our applications, some of the use cases that they have used already TornadoVM for hardware acceleration of Java applications. This work has been funded by the EU Horizon 2020 Elegant project, and we are collaborating also with Intel to bring one API in the Java ecosystem through TornadoVM. Thank you very much.